Welcome. In this video, we're going to take a quick look at some of the techniques that are used in biomechanics for measuring force. Now, in some previous videos, we've talked about kind of the definition of force and how measuring force directly is very difficult to do. Most of the time, what we're actually doing is measuring what the force is doing, or the interaction between two objects. And some of the typical ways that maybe you've measured force in the past and maybe not known it is when you step on a weigh scale, or use, let's say, a spring scale that would be used for measuring fish or meat or things like that. And these scales, although they're pretty basic, use a pretty standard method for measuring force. The concept that the scales are based on the fact that all things deform. Now, in most of what we're doing, we're going to be talking about rigid bodies, but when we're measuring forces, we're actually depending on the fact that everything is not rigid. So I've got a picture of a spring there, and if we apply a certain amount of force to that spring will stretch. And so we'll call the amount that it stretches, we'll call that the deflection. And it turns out that the amount of force that it takes to stretch a spring a certain amount, or to deflect a spring, the deflection and the force are actually related, and they're related in a pretty constant way. So if we were to plot the amount of force versus the deflection for a spring, let's say, the plot might look like that. So as long as we're not stretching the spring so that it deforms permanently, the spring will spring back, and if you pull it again, you'll get the same kind of relationship between force and deflection. And it turns out for most of these types of ways of measuring force that the deflection and the force are linked by a constant. So in the most basic sense, it would be a formula like this. So the amount of force it takes to move the spring a certain amount is equal to the displacement times some constant, that k value. So on the graph, it would look like this. You apply a certain amount of force, you get a certain deflection, and if you double the force, you get double the deflection. And so if you can figure out what that relationship between the force and the deflection is for the spring that you're using as a measuring device, then you can calibrate that, and then you can go the other way. So you can look at how much the spring deflects, and you can estimate what the actual force was in order to make that displacement. A spring scale like this is a pretty good example of that. So you apply a force on the end of the spring scale. The spring stretches, and if you've got the scale calibrated, then you can measure how much the spring deflects, and you can estimate how much force was applied to the spring. And this is exactly the same kind of concept that you get in most bathroom scales. Instead of a straight line spring, you've got a coil spring, but it's the same kind of thing. So the scale's been calibrated so that when you apply a force to the scale, it deflects the spring a certain amount, and the amount that it deflects is related to the amount of force. So in the previous examples, we used a spring so that it's easier to visualize what's going on, but it doesn't have to be a spring. If you recall, when we were talking about rigid bodies, in fact, all materials, all objects deform to a certain amount when force is applied to them, and that would include things like even metals like steel. And this concept's used to make electronic force transducers, and they work very much on the same principle as the springs, except they just don't deform as much. So they use a piece of steel, and when force is applied to that steel, the steel deforms a very small amount, but the sensor uses very sensitive methods for measuring that deformation. So even though when you apply a force to that force transducer, it doesn't deform very much inside, the deformation is still measurable, and it's still related to the force applied. So electronics can be combined in there, and we can actually measure force electronically that way. And quite often in biomechanics, we'll use a force measuring device called a force plate, which is essentially a bunch of those electronic force transducers all assembled together in a flat plate-like device that's often embedded in the floor, so that when a person steps on the plate can actually measure the forces that they apply to the ground, so the ground reaction forces. And usually the plate is set up in a way that it can not just measure the vertical force, but it can also measure the anterior posterior force and the medial lateral force. And so this makes the force plate an essential tool in biomechanics. It's used extensively to take a look at how the force pattern changes over time as somebody's stepping on the plate. In this example, this is an example of what the ground reaction force looks like during the stance phase of walking, and showing the vertical, the anterior, posterior, and the medial lateral forces during that time.